Thank you. Thanks so much. I hope you guys are enjoying yourselves. I hope you've seen the DJ who's being powered by the bicycles that you guys can all ride. You can learn how to tie knots. You can see a motion capture suit in action with a real athlete inside of it. Our friends from Nike brought some amazing equipment, high-speed video cameras that will show you things you never ever thought you could see coming out of your own body, and a pressure plate that shows you what it looks like when you step on the ground or take a step as you're running. So have a lot of fun. We're really excited to have our featured speaker here tonight. He is Senior Director of the Nike Sports Research Lab.
And respond to things at an unbelievable rate, and we'll talk about that a little bit. And we tap into all this knowledge to make unbelievable product and experiences, as hopefully most of you have already seen. Hopefully Nike's not a new concept for most of the people in the room. So you can't talk about Nike and you can't talk about sports science without first talking about Bill Bowerman. And for those who don't know, he was a track and field coach at the University of Oregon. And he was the co-founder of Nike. And I think more importantly, he was Nike's first sports scientist. He obsessed the details. He was an experimenter. He was an entrepreneur. And he constantly tweaked training and product to make his athletes perform at the highest level. And we continue the essence of everything that he does through to today. And our mission basically is to bring inspiration and innovation to every athlete in the world. And the asterisk is super important, and this comes from Bill Bowerman himself. And he always used to say, if you have a body, you're an athlete. He coached elite runners at the University of Oregon, but he also wrote a book about running and tried to get the masses to start exercising and being healthy. And And he didn't really take any excuses for an answer. If you have a body, you're an athlete. And that's how we approach it every single day. And as Jason mentioned, we have the luxury and the pleasure of working with some amazing, elite, very sort of famous athletes, but we also have the pleasure of working with people just like yourselves, because at the end of the day, you two are athletes and you're the people that ultimately buy and use our product also. So we work across the spectrum. Another core belief of everything we do is everything starts and ends with the athlete. It sounds cliche, but if we're doing it for other people other than athletes, we're not being true to what we do. And there's a few different groups, and I'm going to focus on the science and focus on how we apply that to the innovations we do, but there are certainly other groups. We have a group called Spark who focuses on what are the right scientific methods for training an athlete, for knowing when they're ready to train, and how do they recover and perform at the highest level. I'm not going to talk much about that today, just knowing that there's a group that does that. We obviously have a digital group that focuses on sort of quantifying and measuring athletes and providing feedback and information and experiences back to athletes. And of course, we have a product team. We have an unbelievable team of designers and builders and makers and thinkers who at the end of the day keep the lights on for us. Because certainly what we do drives the innovation, we hope. But when you see something and it's a really cool color and you say, wow, what's that? That's those guys, and they're unbelievable. But it all starts and ends with the athlete. Our mission, quite simply, and I'll sort of get through the boring stuff, but I want to drive home, we provide the scientific understanding of athletes and the environments they play in. And when we say scientific understanding, if you think about, take a sport, take different sports, the demands that different athletes have in different sports. The difference between playing soccer and the difference between playing tennis. Or playing tennis, as we see right now at Roland Garros, on clay versus grass versus hard court. Or what are the differences between males and females? Or the difference between skill level or age. What does an 8-year-old tennis player need? Or what does a 17-year-old obsessive soccer player need? And so there's no end, because there's a constantly evolving set of work that has to be done, and sports and people continually evolve. The lab itself was started in 1980 in Exeter, New Hampshire, so we also have the luxury of having 35 years of knowledge to tap in and build on. But there's no shortage of ideas, and there's never a lack of a new idea or a new goal or some crazy hunch that we're going to go after to help change performance. The one thing we don't do, I mentioned this earlier, is we're not responsible at all for the aesthetics or how we make it or how much, how sustainable it is, or how we do the manufacturing. Because if we were, I wouldn't be here talking to you today, because that's not my area of expertise. We're the researchers. We have roughly 35 people in the Sport Research Lab, and I can't emphasize enough, it's an unbelievable, talented group of researchers. 17 of those have PhDs in the respective fields. We have 4 scientific disciplines that we primarily work in. Everybody else has advanced graduate degrees, most of them sort of masters of science in their particular fields. Biomechanics is a group, that's how I was classically trained, and the definition of that is, the academic definition, if somebody was going to tell you that, is it's the study of the forces on your body and how you respond to those. So whether you jump and land, and how do you respond to those forces, or whether it's changes over time, whether it's changes in the muscle or the bone, or how you respond to different products, that's biomechanics. We have a physiology team who studies the internal regulatory mechanisms. So when you get tired, when your muscles get sore, and how do you breathe and take in that oxygen, or how do you regulate temperature on a hot day when you're running sort of up and down the pier and it's getting hotter and hotter and hotter? How do we understand that, and ultimately how do we affect that to make you a better athlete? The sensory perception team essentially looks at what we call the drivers of liking. And we can give anybody 2 of anything, give you 2 shirts, give you 2 sausages, give you 2 whatever you want, and say, which one do you like? And you'll choose one. But if I ask you which one do you like, you'll actually start changing the way you answer that question, because if you don't know how to verbalize why you like it, you might choose what's easier to articulate. Right? So just the ask of acting you is there's a science in how we actually extract that kind of feedback. But ultimately we want to know what is it inside, whether it's cognitive or at the sensor level, makes you choose one over the other. Is it the touch? Is it the feel? Is it the smell? And the example we like to talk about is wettedness. We like that, it's just a funny word, wettedness. right? But if you take skin wettedness, you don't have a sensor in your body that responds to wet. You have thermal sensors and you have pressure sensors, and the combination of those two in your head tells you this is wet. So if you understand which of those two in combination makes you feel more comfortable in a wet, clingy t-shirt, we can start to manipulate those things, because it's hard to keep you drier, but I can certainly make you more comfortable. That's the drivers of liking. It's not just walking through retail and just hand touching everything as you go by, like lots of people like to do. I like that one, I like that, I don't like that one. System science is essentially a group that does a lot of data mining and data modeling for us. Because as we get into it in a little bit, ultimately, we're all individuals, and we all respond differently to the kind of things that we do to us. So today, just for brevity, and it's something that everybody likes, every athlete, whether you drive a car, whether you perform, every athlete wants to be faster. So I'm going to focus the rest of this on speed. And we talk about speed in different planes. There's linear speed, there's acceleration or top speed, there's multi-directional speed, which some people call agility. There's vertical speed. Ultimately, it's how high you jump. There's a vertical component. But you ask any athlete, what would I like to do? I'd like to be faster, right? They might tell you I'd like to play longer or be less injured, but crucial to every sport. And one of my colleagues at Nike, who works in the innovation kitchen, he always likes to use this example, and so I've, full disclosure, I've stolen it from him because I like it. But you can't design for what you don't understand. If you can't conceptually understand the problem you're trying to solve, it's very difficult to apply design or solution to solve the problem that you're trying to do. And the first cars are a classic example of this. Finally figured out how to get rid of the horse, so we designed a car that looks exactly like a horse carriage, because we didn't understand any better. And it was funny, somebody mentioned to me earlier, it's actually a really good design, because in the event that it breaks down, you just put a horse back in front of it and you can still get home. But we even called it a horseless carriage. And it was an unbelievable sort of step in sort of human transportation, but it looks like a horse's carriage. And it's understandable because you just don't know where to go. Fast forward 40 years, 1934 Alfa Romeo, we start to understand combustion engines a little better, and we have what is, by even today's standards, a high-performance race car. And we're starting to understand aerodynamics, but we don't have sort of the jump on a bike and get your wind tunnel thing done right outside the room back in 1934. We don't. So we rely on shapes. You know, an arrow looks faster, looks more aerodynamic. And you can imagine, it looks aerodynamic, it's not that aerodynamic, and certainly there's very little safety built in for the passenger. Because again, you don't understand what's going on, so it's hard to design these things. And of course, if you fast forward to today, you have these engineering marvels. I mean, it's absolute data-driven design at its best. It's everything about these cars today is functionally driven. Somebody gets to come in and slap a Vodafone on it and a mobile, or maybe we're going to highlight, do yellow. Yellow looks good on the tires. But everything about this car is driven through data for the goal of making this car go faster. All right, pretty straightforward. And you can apply that to a lot of things in industry. But what if the system was responding every time you tried to put a design against it? What if it adapted every time you put something against it? And what if it adapted or responded in an unpredictable manner? And that's the reason that I have a job today. It's the bio part of biomechanics. It's because we all respond differently, and we respond in an unpredictable manner. And what if this is the canvas you have to work on? Right? And it's Ashton Eaton. It looks good, right? World record in the decathlon, gold medalist in the decathlon. But what if every time you tried to do something to make him faster, even if it made sense, he responded it to in a way that was unpredictable, that you don't know if he's faster anymore? Makes it very hard to predict. And if it was, we'd be replaced by those, if you go into IKEA and they have that thing that's just pushing on the cushion over and over in the front door, and it can show you can take 1,000,000 compressions. It's not what the body does. Think about when you run or when you land. If I jump off this table and I'm barefoot, I can land. I can land from a really high table. We used to do it as kids. And yet, if you do it multiple times over a long duration, you need cushioning. And as soon as I put cushioning on you, you actually change the way you land, because you have these built-in springs in your knees and your hips and your ankles and the ball of your foot, and you do this immediately. And if you don't even need to know you're going to land to know you're going to change your strategy for landing. So it's not as simple as saying, I need cushioning, let me just put something underneath and see what happens. That affects everything else that I do. It affects how I move, it affects how I fatigue, it affects everything. So we're an unbelievable system. Imagine if you're running and you're going down sort of concrete and you see a grassy patch. You know ahead of time that that grass is softer, and so you will change your stride, mid-stride while you're in the air, change the way you move, land on the grass, and change back to your stride pattern on concrete. I mean, it's unbelievable. And you can do some fancy tricks to fool people into this. You tell them it's soft, but it's actually really hard, and you get one shot at that. You get people running in, they think it's really hard, and they go, boom. And they go, but then they don't make that mistake again. It's very hard. You can do subtle things with trapdoors, but understanding how the body responds is the greatest challenge that we face. So if you go and you take a very simple, pragmatic approach to what we do at Nike, and you say, well, what are all the things that I can affect by the products that we build or the crazy ideas we can come up with? I can change the traction underneath. I can change the cushioning. I can change the fit. All right? Sounds pretty straightforward. We can tweak the joints. We can put stiff plates into shoes and change how stiff the joints are in the ball of your feet. We can change how stiff your ankles are. I can change the range of motion and stiffness of your hips and your knees and other joints further up the body. We can add weights or reduce mass and change the inertia of the segments. So if you're kicking, and what if I add extra mass at the end? What does that do? We can change the physiology. So if we change the way you sweat, or the way you sort of have thermal regulation, or the mass, or how you build up fatigue, or the damage to the muscles, the work that you're doing. And ultimately, we can also change how you feel and respond to these things, which is also super important. If you feel like it's going to make you faster, you probably will run faster in those things. Right? Perception is a huge part of what we do. So we take a very pragmatic approach. We try and understand form, force, and fatigue. And again, just so I'm being truthful and honest, I borrowed this from Lieutenant Hick he works with DARPA. We used to say kinematics, kinetics, and fatigue. It's a lot more catchy. It's the 3 Fs. So form, force, and fatigue. And then we do this through the lens of performance, protection, and perception. And that's it. That's all we do every day of our lives. And I got to tell you, it is the best job I can think of. It's awesome. So we go through and sort of show you some of the tools we use to understand the body in motion. And when I say tools, and certainly there's a lot of tools in here, most of you know this, but you can't define yourselves by the tools that you use, because tools evolve. And people have heard me say this, we use a scalpel analogy. Your tool is only as good as the people who run it. I can buy a $200 scalpel, and there's not a person in the room who's going to let me open you up. But a person with the right training, sure, you're going to sit down, or not willfully, because nobody wants to do that, but you'll trust that person. And so we never define ourselves by the tools. We define ourselves by the people, and more importantly, how we apply those tools to innovation. But I'm going to show you some of them. So very similar to the system you see outside, and if you haven't seen it, I encourage you to go check it out, because it is super cool. We have 3D motion capture systems, and basically, wherever we put markers on the body, and there's certainly other ways to do this, but you can capture and quantify the movement of every joint in your body, every segment, every joint. And as soon as you know the motion, you know the relationship between them, so you can get joint angles and velocities and accelerations and the timing between those things. And after that, we're limited by our imagination. We can put it on you and have you do skateboarding or skiing or wushu or basketball, soccer, you name it. We use force plates. And a force plate is essentially, imagine a very expensive, very sophisticated scale. And when you step on a scale, it measures how much force you put down into that scale. It tells you how much you weigh. This is a scale that takes 10,000 measurements a second in 3 dimensions. So we get the force you put into the ground, not just vertically, but forwards and backwards and side to side. Because even if you take something like landing, everybody thinks, oh, I land. If I jump off here and land, it's a vertical force. True, but you have a huge forwards and backwards component to that force, which affects how you respond and affects wear and tear on your joints. We also get the location of where that force is underfoot, and you can see on the picture up here, the red arrow sort of showing sort of a magnitude of the force, the direction of the force, and where it's located exactly under the foot. And I'll tell you why we do that in just a moment. High-speed video, and if you haven't checked out some of the people I work with outside, they've been shooting high-speed video, and everybody's taken the violent option of punching each other in a high-speed video. We had other things set up, but Jason mentioned it. We call it, it's like making sausages. You know, you like to eat them. You don't always want to know what goes into them. High-speed videos is like making sausage. It allows you to see things you can't see with the naked eye. And we do it not just qualitatively, but quantitatively also. There's ways we can sort of combine cameras and digitize what happens and extract meaningful information out of these. And just a note on the high-speed cameras, the ones we have outside, if you go to a movie and you watch a digital film, you're seeing 30 frames per second. Unless you went and saw The Hobbit, then you saw it a little bit faster, but most often it's 30 frames a second. We can do 30,000 frames a second, so you can imagine what you can see that you won't necessarily pick up with the eye. Also outside, we have examples of pressure measurement tools, which lets us measure the interface between your body and whatever we put under it. But we have some of these that we can also put into shoes, and they're wireless, and we can send you out and let you go play your sports. And we get that information back, and it helps us evaluate how the anatomy of your foot responds to the cushioning or the cleats or the fit or whatever we're putting underneath you. And again, you're limited by your imagination. We can put these anywhere on your body. 3D body scanners. They have some super cool examples of, you know, if you haven't had your head snapped out here and sort of had it sent back to your phone, I encourage you to do so. We use 3D body scanners to look at the anthropometrics of the foot. If you look at different regional differences or ethnic differences, our feet are very different. And we're a global company that needs to sell product across the world. So if we look at feet in Asia versus South America versus North America versus Europe, we can very quickly scan and get more measurements than you would ever want to know off your foot. And we apply those to how we build and sort of ensure adequate fit for different sports. Physiological measurements, again, we measure what's inside. Thermal cameras, skin wettedness, temperature, oxygen exchange, just imagination. And then when we don't have expertise, we partner with other groups. When we don't have access to certain types of athletes or certain types of equipment, an example here, we partner with a hospital in Detroit using advanced imaging techniques to actually look at the foot inside the shoe. And we can do 3D reconstructions of the bones, as you can sort of see it's the talus, one of the bones in your ankle, and what actually goes on inside the shoe. And as much as you might look at this and sort of look at what I'm wearing on my feet, that is what goes into our performance product. So when we put it all together, we're able to take an Olympian like this person coming out of the blocks, and we can quantify motion in ways that you would never believe. We can calculate for every joint in your body how much load is on that joint, how much torque is in that joint. So imagine if I do this, there's a torque at my knee that I have to resist to be able to come back up. We can tell you where you lose energy, where you produce energy. We can have you swing a golf club and tell you how much torque is on your spine. The magic is what do you do with that and how do you apply it? But looking at this, and this is the force as they're sort of running across. If we know, imagine, I use a door analogy, if I know where your body is and I know where the force is, if you go up to a door far from a hinge and you push on the handle, door swings open because you have a big distance between where you push and the hinge. If you get really close, it's a lot harder to open the door. You have to apply a lot more force. It's the exact same in the body. If I have a big force beside my, if you look in this plane, sort of on the sagittal side plane on the body, when I come down and jump up, if I can increase that lever, as long as I have the strength to withstand it, I can maybe improve performance. But if you go in a plane where your joints don't want to move, so people who run and they talk about I have knee pain, you can have a force inside or outside of your knees, and it's trying to create a torque at your knee, but your knee doesn't want to go that way. So after you come home from a run, you say, well, inside of my knees are sore. And again, if we can quantify it, we can build product to correct it and help you perform longer. So when we put it all together, we have the ability to capture, to analyze, to visualize, and then to apply these insights to the products that we build. And we work closely with Autodesk on developing tools where we can sort of enhance our ability to do this. And as you can see here, you can see visual displays of pressures underfoot, forces underfoot, and forces at each of the joints as you go through a simple movement like jumping. Now imagine doing that in a game with different players, different interactions. So some people say, well, hey, that's a lot of work. It's just shoes, right? You know, and I think one of the things they said in the announcement here is athletes are evolving. And I like to use this example. If you think about sort of the evolution of athletes, we're all bigger than our grandparents. And like, we eat better, and there's better medicine and all that kind of stuff. We got hormones in the milk, what have you. So the athletes are changing, right? We know that. And the stat that I like to get, I talk about two different things. One of them, there's a study looking at NBA players, and if you plot the growth of the human race against the growth of the NBA is growing 4 times faster than the human race, right? So they're getting bigger. If you look at an NFL lineman in the 60s, and you compare them to the average male population, height, weight, BMI, sort of anthropometrics, about 15% of the male population look like an NFL lineman. If you do the same comparison today, it's 1/10%. So these athletes are getting unbelievably strong, unbelievably fast. Talk about the 100-meter race. There was a great infographic in the New York Times a few weeks back that showed a really cool visual of this. But for the longest time, it was above 10 seconds. And the idea of crossing the 10-second threshold was just unbelievable. And we didn't actually do it until 1968, and there were some advances in tracks, some advances in product that helped that happen. But if you tell somebody, I think today we're at 9:58, what are you saying? If you say to somebody, hey, one day we're going to break 9 seconds, people shake their head. But we're going to get there. And as you run faster and as you change the forces that you generate and you change how your body is, the demands of the game change, which forces us to adapt with those. So when the question is, hey, can I still wear my Chuck Taylors from 1960 to play basketball today, I wouldn't advise it. Take vertical jump. And a long time ago when I was in school, it used to be that 30-inch vertical jump was the pinnacle of success. And I never got there. I was like 28 inches. It was like I was always short. It was my problem. But 30 inches was considered elite. Today, routinely, you see people with a 44-inch vertical. Same token, when you say, hey, we're going to start jumping 60 inches, people say, no, 60 inches is crazy. There are people, we've had people in the lab who jump high 50s, and there are people in popular media. There's a basketball player out there, you can YouTube him, who has a 58-inch vertical. You only have to go back 20 years, and people would think that guy was Superman. He'd be wearing a cape, jumping from building to building, right? It's incredible. We're evolving very, very quickly, and the product and the science has to meet the demands of those evolving athletes. So I'm just going to show you a couple examples how we've applied this knowledge to this goal of going faster and going faster longer. There's sort of an implied, hey, I want to have a faster top speed, I want to run faster, but I also want to sort of look at endurance. And one of the examples is the pre-cool ice vest. And we had a gentleman in the lab, Dr. Lauren Myrie, who was one of our physiologists, and he was doing a lot of work looking at one of the factors that limits performance is increase in temperature. And when you go out for a run, your core temperature rises. I'm a Canadian here, so I'm going to be guilty of using Celsius, but if somebody can convert, I always forget. So 37 Celsius is essentially core temperature. It's 98.6. And when you start to exercise, your temperature is going to rise. So if you plot it over time, there's a slope of rise of temperature. And it happens for everybody. And you can train and it'll get better. Somebody who runs a marathon in 2 hours and 6 minutes has a different slope than I have. But when you reach a critical core temperature, you start to boink. And there's actually a physiological reason you boink. There's a lot of things that happen internally. Okay? And what he found was that by pre-cooling the body using these ice vests, you can lower the core temperature to a level that doesn't inhibit performance early, and you don't change the slope of the rise of core temperature, but you just delay that offset. So you might start here and go up, or you can start here and go up, and it was really successful at changing performance of some of these athletes. In fact, we had non-Nike athletes sort of ducking in the corners, putting these things on before the marathon in Athens. So one example of how you apply, and sort of obviously not something you saw commercially. You didn't walk into Foot Locker and say, do you have an ice vest and an extra large, please? But an example is sometimes how we just change performance. Just geeking out here for a quick second on sprint plates. One of the reasons when you see sprint plates that they have that stiff plate in them is one of the things we know is that as your foot flexes, as your foot does this in sprinting motion, you actually bleed energy at that joint. It's called the metatarsal joint. I always call it the ball of the foot. Right? So the ball of the foot, you bleed energy as it flexes. It's not a lot, but in this sort of 2% of the total energy range. So the idea of stiff plates is the stiffer you make them, the more you turn off that leaky faucet. So you're getting better not by putting more in the system, but by preventing more loss. Again, the trick here is not every athlete responds the same, but that's the science behind sprint plates, and that's the science that led to the Zoom Superfly that we had at the Olympics last year. And obviously we had a level of success with our athletes in the Olympics. But you know, there's a number of technologies that go into this beyond the plate. Obviously there's lockdown, there's a weight, there's a construction that we're able to achieve with the use of flywire and how we lock the foot down. But the plate stiffness is driven from the work that we do to help improve performance with athletes. Recently, and some of you may have heard of this, we went one step further. And as technology evolves, we released the first laser-sintered shoe for the Combine in the NFL Combine this year. And this was an unbelievable story because by using laser sintering and sort of evolving with the tools that we use to do the research, we were able to iterate much, much faster and do many more trials on athletes with the sole goal of making athletes faster in the Combine. And you can think, like, for these athletes coming out of college, the Combine, especially running the 40, is the defining moment of their career. I mean, if they come out and absolutely blow it away, they're going to move up the draft rankings, or they could completely fall out. Right? It's the single moment that defines what they're going to do going into college. So we worked on a shoe, not to play football in, but to make you faster in the Combine. And the amazing story here, you imagine this moment, the stress, like you get to go up and this is it. We made 24 pairs of shoes, right? Sort of did a limited run. We handed them out to certain athletes. 32 people ran in those shoes in the Combine. So word was getting out that these shoes were pretty good. And can you imagine a shoe you've never run in and you're about to have the, hopefully close to 4 seconds, not close to 5 seconds of your life, and you're going to put on somebody else's shoes and say, hey, I'm a size 10. Can I borrow those for a second? And you go out and do the thing. So unbelievably successful, but also a key milestone in how we sort of, you know, look to the future to build, evaluate, and ideate around performance innovation. And if you haven't seen them, you can check them out. You can Google them. They're on our website. But amazing advances for us. So I'll wrap it up with this, and I'd say, you know, basically our job is we deliver proven insights to drive athletic performance. That's it. That's the end of my job. And in the future, you know, these insights, as these tools like we just saw evolve, that's going to be the currency that separates us. It's going to be the currency that separates anybody. It's what you do with the tools, not the tools themselves. But as I was talking, and I was talking to a colleague of mine, Dr. Paul Zare, who writes these books combining science and superheroes, you know, becoming Batman, inventing Iron Man, and we were talking about there's a very famous Steve Jobs video that floats around where he talks about looking at the economy of human movement. And he was bummed out, and he's talking about, you know, humans were way down our list, and the condor was way up here, and for these amazing intellects, we're remarkably pathetic when it comes to efficiency of movement. And he had this moment where he discovered that somebody had actually looked at the economy of humans moving on a bike. And he had this epiphany of and he sort of describes it through the lens of his computers, but we have the intellect to build the tools that allow us to be more proficient, and then we smoked the condor. We were way better because we have this. We have opposable thumbs, too, a little thing the condor doesn't have, right? But what happens, and I was talking about this with Dr. Zare, when the tool that you use is your body and not the products you put on it. It's also one of those things we look forward to, and I've, you know, certainly I was fortunate enough to be at a conference here at Autodesk where we talked about the future of using your body as the tool from the inside out, not the outside in. And that's sort of a brave new world that we're all looking towards. And as these tools become more ubiquitous and everybody's wearing them and you can do this with your iPhone, what happens when we start changing it inside? And how does that affect? We already see the rapid change in humans and performance and the evolution of athletes, but there's probably a lot more to come that none of us can predict right now in the next 40, 50 years. So I'll leave you with that ponderable, and I'll just say thank you.
Awesome. You all may never look at your shoes the same way again. I think we're going to take just one or two questions. So if anybody has a question, let's let them roll. Anyone?
Have you seen any breakthroughs in shoelaces for form and fit?
Shoelaces by themselves are one method of enclosure. And certainly, you know, there's different methods and you fight what's aesthetically pleasing. We have Velcro straps on some of our track spikes that need lockdown. Certainly, if you look at our dynamic fit, the way you construct a shoe, independent of shoelaces, changes how it locks down. But ultimately, it's what are you trying to lock down? Are you trying to prevent slide? Are you trying to prevent forward slide? Because if you imagine like a car accident, you don't want something that absolutely prevents movement. You're either going to take all the force in the skin, or you're going to have these repetitive stresses. And I'll just one quick example. If you imagine a cut, you come in and you make a cut, somebody goes, and you're watching the NBA Finals, which are on right now. Every time you cut, there's 2 to 3 times your body weight of shear force. And so ultimate lockdown is not always desirable, but there's a lot of closure methods that we have and that we're working on that change that. Yes? Are we just doing 2 or?
This might be a big question, but I'm curious on how research works with the designers. Like if you come up with all the ideas and then you just like, here's our ideas, design, go to it, and if it goes back and forth, or kind of what the relationship is.
The relationship is awesome, but like any awesome relationship, it's like being married. There's good days and bad days. No, but it's fantastic. We love each other dearly, but we argue sometimes. And the way innovation is structured at Nike is we have different groups, and we have a group called the Innovation Kitchen, which is design and manufacturing, and they're unbelievable. We sit in the middle between there's a development side, a design side. There's also listen to the market. What does the market want and desire? So it's not a linear process. You don't have an idea and then do the research and then build it, test it, and get it to market. It's the most chaotic experience, but out of it comes these beautiful ideas. And so certainly ideas can come from us, but frequently ideas come from design. And the best, most rewarding experiences are when we have a design or we get a cue from an athlete about what they want. And we have the science, but designers can think about how to apply that in ways that we can't. And that's when it's really rewarding. They'll say, oh, I get it, but I think we should do it this way. And there's just these light bulbs go off. I mean, it's magic. But it's like a marriage.
We'll take one more question.
Sure. Well, we got to go to the back of them. Okay.
You talk about sustainability, but we have to throw away our running shoes pretty often because they kind of get weird. Have you looked at making them last longer?
The easy answer is yes. The more complicated answer, we can chat offline. I'll just say sustainability is crucial and hugely important in everything that we do. And we could talk more about it later. But absolutely, it's key to everything we do. I think if you look at Flyknit, was a great example of reducing waste in a shoe with the focus of doing exactly that. We always have the planet in mind, always.
I'm getting heckled for one more, so it's back
here. We didn't go to the back of the room.
So I'm really curious as you get to a place where you speak of tools and the ubiquity of tools and the availability of tools, but at the same time you operate in a very competitive market. I'm curious about the tone and contour of ethical conversations as you start to think about how we create these tools that are not going to be immediately sort of delivered at parity across all the landscape of athletes. You're going to have 24 shoes, 30 guys scrambling to get them. What about the others? How do you sort of think about how the work you do informs the ethic of sport and is informed by the ethic and the dialogue you have between research and product?
That's a complicated question. I'll give you a relatively simple answer, is that we think about it. So from the ethics of research, we certainly consider that. From the ethics of how we distribute product, there's also a reality of supply and demand and what we can make in a productive, sustainable way and provide to athletes. We certainly don't do it in a way of trying to discriminate, but we also have this mantra of trying to do work that benefits, if you have a body, you are an athlete. And so we try and cut across the spectrum.
All right. Please join me in thanking Matt Nurse. That was great. Really great. So, and a big thanks to Matt and his team, the folks at Nike, for bringing some of the demos they have outside. Please try them out. They're really great. Just a couple other things. Get one of these stickers. The way you get that is either by riding the bikes, which is powering our sound system tonight, or winning a feat of strength. So find our roaming feat of strength expert. We're taking July off for Design Night because it's July 4th, but we hope to see you guys back here August 1st. The theme is music, and we're going to rock and roll with you guys. So thanks a lot.